All right, so my goal will be to present a proof of Bike-Dieck-Johansen theorem. The proof that I've chosen is easily modified to handle, for example, the exclusion processes, the task step for the step initial condition, and it's fairly generic. The proof is roughly 10 years old, maybe 12, and I should warn you that over these years I've seen more than once and twice how people get disappointed when they see the proof, especially probabilists. Now, the reason they get disappointed is not because the proof is terribly hard. Hopefully I'll convince you that it's not. The reason is that the proof looks ad hoc. It looks like a sequence of surprising coincidences, some luck that eventually leads you to the final statement. And this is the way it was sort of viewed for some time. I will address this issue tomorrow. So tomorrow I will try to reverse the direction of ideas to not to start with a probabilistic problem and then to look for its algebraic solution, because that ends up being ad hoc and somehow miraculous. Instead, I will try to take an algebraic structure and produce out of that algebraic structure a probabilistic model. In that direction, it's, well, not quite algorithmic, but much less surprising that you get something in the end that you can analyze. So that the issue of why this works and how one can modify it to cover more problems will be addressed tomorrow. And then later on, I'll show in the 5th lecture how this philosophy led to the solution of the problem of asymptotics for finite temperature polymers. And there is plenty of room there to explore, I should say. Meanwhile, for today, what I will try to show is why a connection of the probabilistic problem with the algebraic structure is useful. How that structure actually allows you to obtain information on the probabilistic quantities that is far beyond what one can get through probabilistic methods, at least the methods that we know for now. Right, so this is the general outline. And the main object for today has a name. The name is Schur measure. And it is defined through the Schur polynomials that you may have seen in the session of Vadim Gorin. I'll write the definition. So if one has a partition, which is a weakly decreasing sequence of natural numbers of finite length, I'll denote by L of lambda the number of non-zero coordinates. Then the Schur function evaluated, the Schur polynomial evaluated at a finite set of variables is the ratio of two determinants, xi lambda j plus n minus j, divided by the same determinant with all lambda 0, the determinant of size 1 to n. And this is in case the number of x's is greater than the number of different lambdas and 0 otherwise. So if the partition is too long and you don't have enough x's, then this is 0. So this part, so this is not a rational function. This is actually a polynomial. This is a van der Monde determinant. It's easy to see that this thing is divisible. You get a symmetric polynomial in x variables. The Schur functions have the convenient property that if one takes the Schur functions extended by 0 in this way, that if I add 0 at the end, then I can remove it. This is the stability property that's necessary. And this property allows one to talk about Schur polynomials and infinite linear variables, which I will try not to do too much. Then there was something that, again, Vadim mentioned, but that's also not hard to prove. that if one takes the sum over all partitions of the product of two sure functions with the same index evaluated at a different set of variables, then there is a nice expression at the end over all ij, where this should be understood as an expansion of this thing in the geometric series. So if you expand it into geometric series, you multiply them, and you collect the terms differently, you get the left-hand side. And that's not hard to prove. So this identity here, even though you can just prove it as a formula, has a representation theoretic meaning. Namely, if one looks at the set of matrices with two groups acting on the set, one copy of the general linear group acting by multiplications on the left, the other by multiplications on the right, then you can decompose the space of polynomial functions on matrices into irreducible representations with respect to that action, and taking characters of both sides produces this identity. So there is some materialization of this identity in representation theory, but I actually don't need it. So then the definition is that a sure measure on partitions assigns weight. So I'll write probability of lambda. Now this probability should be taken with a grain of salt. This probability may be negative. It can also be viewed as a formal object. If I view sure functions as formal objects in infinitely many variables, then this probability will live in some completion of the space of formal power series and so on. But I'm not going to concentrate on that. In the particular case I'll be interested in, this will actually be probability. So this is S lambda of x, S lambda of y, divided by that product. The definition itself was given by Andrei Kunkov in 2000, generalized in certain other examples of measures on partitions, the Plancherel measures that I'll talk about, and the Z measures that are related to the material of Grigory Leshansky course. And they realized that this is really a useful general notion that one can deal with, and it's been very popular and successful. Now how to relate this thing to what I talked about yesterday. Now yesterday there was a Poisson process, and I produced some sort of a shadow line construction, you may remember, that eventually produced a partition. So this was a Poisson process with density 1 that I'd restricted on a square of size theta by theta. And using some line construction, I produced a partition sort of sitting at this point, such that its first part was actually the last passage percolation time. Last passage percolation time, in the sense that it was the maximal number of locations of Poisson points that I could collect using upright paths from the corner to that location. Now the distribution, what I stated without proof, was that the distribution of that partition had the following form. Was dimension lambda. So absolute value of lambda is just the sum of all coordinates of lambda, theta to the power 2 absolute value of lambda. Where this dimension of lambda was the representation, theoretic dimension for the reducible representations of the symmetric group, or the way I defined it independently it was the number of paths in the Young graph from the root to this diagram lambda. So the number of paths was this dimension lambda. Now here is a little lemma that matches this object to this object. And the lemma is that if I take the limit of a sure function with many coordinates, each of them is small, but the total number of coordinates is large. Okay, that's enough. And then n go into infinity. Then what I read is going to be theta raised to the number of boxes times the dimension lambda over. Now you can see that. So if I put this, let me write this a little bit, theta lambda and all this squared, and this is the same thing as being squared in here, right? And so if I go back to this object here, then the Poissonized Plancherel measure that's there is of a limiting form of this expression, right? Now, how does one prove that? There are many ways. First of all, you can try to do it directly. So what is the Schur function? It's the ratio of two determinants. Now, if I put all the variables being equal, the numerator and the denominator will both give zeros, right? If any two x's are equal, then both the numerator and denominator are zeros. So this is some fancy L'Hopital rule. You need to apply this fancy L'Hopital rule. You can actually do it for finitely many x's. That will be equivalent to computing the dimension of the reducible representation of the unitary group. You don't need to know that. You can just do the L'Hopital. And then when you take the growing number of small variables, you can do the combinatorics and recover this object. Okay? I'm not going to do that. You can try. And the proof that I will mention is for people who have seen some representation theory. It's a one-line proof in that case. So you might remember there were these symmetric polynomials or symmetric functions introduced by Vadim. They're called power sums, pk's. Just the sum of all variables raised to the power k. And then to any partition, I can associate another symmetric polynomial, which is just the product of power sums with powers corresponding to the coordinates of that partition. And then there is a formula that expresses Schur function in terms of these ones that are easier to understand. So this formula has the form 1 over the modulus of lambda factorial, the sum overall lambda overall row with this of the same size as lambda. This is the number of permutations of cycle structure rho, or the size of the conjugacy class parameterized by rho. Then there is an object that I haven't defined. This is the value of the reducible character of the corresponding symmetric group on the conjugacy class parameterized by rho. If you don't understand what I'm saying now, it's okay. I'm not going to be using that. You can just do the L'Hopital rule. But I wanted to show that to people who have seen the representations of symmetric group. So this formula actually is one of the most efficient tools to evaluate these character values. There are no explicit formulas for them, but one can use symmetric functions to actually get them. And so in this particular limit that I'm discussing, and let's see what happens to these pk's. Well, you immediately see that p1, if I evaluate it on these arguments, will just give me theta, right? Because I'm summing n numbers, each of them is equal to theta over n. But then p2, p3, and all the other ones will go to 0, right? And so if you substitute this into this formula, then the only p row that will survive will be p1 to the power n. And then if you read off what coefficients you get here, this will be the character value on the unity of the group, which is the dimension of the representation. Okay? So this is where I leave this fact. By just saying that this argument, there are at least 5 different arguments that one can prove this with, gives the reduction of the Poissonized Plancherel measure that I'm interested in for probabilistic reasons to the Schur measure. So now I will deal with Schur measures in general. Right? Well, then I'll do, so here is a informal theorem that Schur measures are determinantal processes. How? The first thing I need to do, I need to take my partition and I need to draw it as a Yann diagram. In what people almost universally now refer to Russian notation. So I'm going to draw Yann diagram rotated by 135 degrees. So the number of boxes in this row is lambda 1, in this row lambda 2, and so on. Now I'm going to project this picture onto the lattice in the form that I already used actually in the first lecture. I'm going to take all segments of slope -1. I'm going to take the middle points of those slopes and project them onto the lattice. Now the lattice that I'm using is actually half integers, z plus half, if I'm taking the middles of the segments. And the set of these points, so the points that I get are going to be given by this formula. Now this is an infinite set, because here my partition eventually ends, but that doesn't mean that my slope -1 segments end, and so eventually I just have a dense configuration here. It should be fairly obvious that this is a one-to-one correspondence onto the image. So if I know these points here, I can reconstruct the Yann diagram. Right? And so then Schur measure, so this picture tells me that Schur measure can be treated as a random point process. I now have a measure on point configurations. Right? So the next thing I want to do, so then my goal, compute correlation functions. If I can compute correlation functions in such a way that I can do some limit transitions, then I'll be able to say something about my original measure. Okay, now I can actually state the theorem. This point process is determinantal. So let me denote by K ij its correlation kernel. So just a reminder, what does it mean? That means that if I compute the nth correlation function, which is the probability for this point configuration to contain to have points at locations x1, x2, up to xn, then this is going to be given by matrix built out of the values of this kernel. So then, if I take the generating function for these values, so this is over all ij that are integers shifted by half. This is a formal generating function at the moment. Then I can write it explicitly in the following form. This is the product of, well, let me write it like that. This is h of x semicolon v, h of y semicolon w. I'll explain what h is. and the formal sum, which is just a geometric progression. K equals 1/2, 3/2, 5/2, and so on, of V over W to the power K. Now, I didn't tell you what H is. So H of, let's say, Z, X and any argument Z is the product of 1 over 1 minus XIZ. So my Schur measure depends on two sets of variables, right? X's and Y's, which are the arguments of these Schur functions. And so they need to enter into the final answer. And so they enter through these H functions, which are products. And also they are, if you follow the symmetric function discussion, they are the generating function for the complete homogeneous symmetric functions evaluated in those variables. Okay? And similarly with y's. So if I put a y here, then I need to use yi here. Okay? Now, this is a formal sum, but it's not hard to extract. So what I need to do now, if I want to do some analysis, I need to be able to extract the coefficient of this object from the right-hand side. If I open the right-hand side as a power series, and that can be done as a contour integral. So let me shift. Well, X and Y are bad letters. So okay, I and J is fine. So if I go with I and J, then I'll just write it in the form 1 over 2 pi root of minus 1 squared double contour integral. So I'm using the fact that if you have a power series, which is, let's say, A of Z, then you can extract AK if you have no convergence issues as a contour integral of this form. So just a simple residue calculus. This can be, well, okay, K is an integer. And that's so I'm doing that twice because I have two indices, and so then I get the same expression here. And then I'll just sum this geometric series, and that gives me this. Now the only thing I should be careful about is that the sum of the geometric series, when it's a formal series, I don't need to care about the convergence. But if I'm writing something like an integral, I need to be sure this converges. And so these contour integrals, they have to be around 0 because we need to pick poles. So here this is around 0. We need to pick the pole at 0. But also I need to assume that the absolute value of W is less than the absolute value of V. The absolute value of V is less than the absolute value of W. So the contours that I will take will just be two circles in the positive direction, one inside the other. Okay. And we'll see that this type of expression is actually very convenient for doing asymptotics, and I'll do the asymptotics once I prove this theorem. Maybe before proving this theorem, while I'll have this on the board, let me just tell you what happens when I take this Plancherel limit. When I use x's and y's, both of this form, so the sequence of x's and the sequence of y's are both of the form n numbers each equal to theta over n, then what happens to this product? So this is the product of 1 minus theta over n z. So all terms are equal, so this is raised to the power n. And I hope everybody knows that this converges to e to the power theta z. And so in the Plancherel case, this formula simplifies a little bit in the following way. This object here is actually e to the power theta v plus w inverse minus v inverse minus w. Okay? And so this is the correlation kernel for the point process associated in this way to random partitions distributed with the Poissonized Plancherel measure. Now eventually, for the last passage percolation time, we will be interested in location of the rightmost particle, because this is the last passage percolation time. But it really makes a lot of sense to introduce this whole picture, because the structure only becomes visible when you get all these particles into the game. You can't just deal with this particle and be happy with it. Okay, so again, I repeat, this looks surprising and ad hoc and unclear in the sense that if you try to generalize, what do you do? That hopefully will be clear when on the next lecture, at least somewhat more clear. Okay, so proof. This identity here, so this identity here, can actually be viewed as a formal identity in power series built out of symmetric functions. I'm not going to bother with doing justifications in that direction. So what I'll just say is that that I will prove this statement for finitely many non-zero x's and y's. It's easy to see that the statement here is consistent with the last x and the last y being set to 0. And so that actually proves rigorously the statement for general symmetric functions. But for general sort of infinitely long x's and y's. I don't need to do that. Even for my application, I can just take finitely many x's and y's and then take some sort of a limit. So I'll be happy with this. Now then, let's think a little. So on the probability of lambda up to a constant, this is the product of two sure functions, or sure polynomials in this case. So what are the sure polynomials? The formulas that I used, okay, finitely many, exactly n capital, let's say. And this n capital needs to be any natural numbers. I can't do it, any natural number. I can't do it for n equals 3. I need to do it for arbitrary n, but then this is enough. So this is my definition, determinant, two determinants divided by two Vandermonde determinants. Now what is random here? So the random object is lambda. This is just the shift of the collection of lambdas. So see, in this picture, in this geometric picture, I'm interested in these numbers. Okay? And what I'll do, I'll introduce the I'm just looking up the letter that I'm using. Well, it doesn't matter. I'll just use the coordinates Lj that are equal to lambda j plus n minus j. This is a different shift. So if you compare that from that, then you see there is a difference of n minus half. Well, just a deterministic shift on the lattice. So if I compute the correlation functions in one set of variables, then the correlation functions in the other set of variables will follow. I should also say that if I have only n non-zero x's and y's, then the sure function, okay, I should say it here. So this is that if the length of lambda is less or equal to n, or 0, if the length of lambda is more than n. Which means that in this picture, the diagrams with non-trivial weight will always live in this strip. Or in other words, I will have this trivial part of the lattice all filled with particles, and then I will have n capital particles that will jump around. Right? When n gets large, then this trivial tail gets smaller, but I will only need to track these big n particles. Anyway, so once I fix, so this is j goes from 1 to n, these are my non-trivial particles, and then I can rewrite that thing as another constant times the determinant of xi to the power lj, determinant yi to the power lj. Right? Now I hope that by now you see that this is a biorthogonal ensemble, whose definition that I gave last time was the determinant of phi. Well, my notation is unfortunate. Let me put it like that. So the definition that I gave last time was determinant of phi of xj, determinant of psi of xj. Well, x's are not the same x's, so think of l's being here instead. And these are our phis and psis. Right? So L is the random object. So phi, actually, yeah. So phi in L, it's xi raised to the power L, and psi of L is yi raised to the power L. Questions maybe. You should really stop me. I'm trying to not skip steps along the way. So if I may be failing that, so you should stop me if you feel that way. Now the biorthogonal ensembles, we already know they are determinantal point processes, and we have the kernel formula for them. So the kernel formula for the biorthogonal ensembles, let me rewrite it in the L coordinates that we had. It was the sum of phi of L1, Cj of L2, G minus transpose L1, L2, where this was the inverse transpose of the Gram matrix. And what's the Gram matrix? G L1, L2. So the Gram matrix is the pairing of these two functions. And what's the pairing? The L here, it's easy to check, it lives on the non-negative integers. So I'm in L2 with the counting measure on non-negative integers. So this is xi to the power L1. This is, what am I doing? This is supposed to be gij to the power minus transpose, sorry. So this is gij. This is xi to the power L, yj to the power L, L greater or equal to 0. You know how to compute that, right? 1 over 1 minus xi yj. How about taking this matrix G? So this is an n by n matrix. Now how about taking this matrix and computing its inverse, let's say minus transpose? Well, one thing we know how to compute. The determinant of G, this is the Cauchy determinant. You might have seen it before, you might have seen it in Vadim's lecture actually, or the TA session. It has a formula. This is I less than j, and this is overall ij. Right? And it's easy to see. Remember, you might remember that for biorthogonal ensemble, my normalization constant was related to the determinant of the Gram matrix. And I actually know this normalization constant here. This is 1 over the product of 1 minus xi yj. So this product is the same as this product. And these two van der Monde determinants I suppressed into this constant. I had them in this picture, but I just moved them into the constant. Now the good thing about this matrix is that any submatrix of this matrix, is if you pick finitely many rows and columns in the same number, is of the same form. So I can compute by the same formula the determinant of any submatrix. But that's all I need to compute the inverse. This is -1 to the power k plus L times the determinant of the submatrix with I not equal to, so I'm computing KL entry, I not equal to K, J not equal to L, divided by the determinant of the full matrix. Now if I use this product formula, I work it through, then many things are going to cancel. Allow me not to do the cancellation on the board. I'll just write what remains. Once I have this on the board, I can actually tell you where things come from. So these factors, so I'm computing the ratio of two expressions like that. One has fewer variables than the other. And so this expression, these factors here, they come from excess factors from the numerator. And these are the extra factors in the Vandermonde comparing to the Vandermonde of smaller size. I hope you can at least see that, but you can easily do the cancellation. All right. So then I have my formula for the kernel, which is not yet in the form that I like it to have, right? So this is the formula I'm aiming for. Okay. Then I have the formula, the sum of those numbers, G, K, L minus transpose. I'm not going to write them down. And then I have, okay. And then I have X. Okay, so K of L1, L2 is equal to this. So maybe I should write, maybe my indices are not the best ones. Xk to the power I, YL to the power J. Okay, where GKL is this expression here. Then the final step. The final step is the residue calculus. This is 1 over 2 pi square root of -1 squared, double contour integral, 1 minus of the product minus WYK, 1 minus ZYK. Now this contour integral should pick up the poles at y's in z and in x's in w. And once I pick up those poles, I will have n terms in n poles in one variable, n poles in the other variable. So I get the sum with n squared number, with n squared terms, and it's exactly this one. You just evaluate the poles, and you'll see that this agrees with this formula. Okay? It's easy to evaluate the pole. You just remove the factor that's blowing up and substitute the corresponding value into the rest. That's it. I'm claiming that this and this is the same. The only thing I need to do is to invert z and call it 1 over w, 1 over v, and I'll get there. Okay? That's it. Now, the lesson that one should draw from this computation. Now, the lesson one should draw from this computation is that we got lucky with the fact that the inverse matrix was explicitly computable. Right? So somehow, the determinantal structure was visible from the structure of the Schur functions, but then to get to the actual formula, we needed some miracle, and the miracle comes in the form of the Gram matrix being invertible in a nice way. Okay? So far, this is just a structural miracle. It just gives you a formula. And so the last thing I want to do is to show how that formula helps to understand the asymptotics of this picture. Okay? So now I forget about these algebraic manipulations. I rewrite my, I go back to this formula. I substitute the Plancherel case. And that tells me that my kernel has the form 1 over 2 pi square root of minus 1 squared, double integral exponential of theta v plus minus v inverse minus w plus w inverse square root of vw, v minus w, dv dw. Okay. So now the question is, what happens as theta goes to infinity? It doesn't seem such a trivial question. This is not the most simple expression you can imagine. But I'll try to convince you that at this moment all the computations can be done in your head, essentially. Let's think about the density function. So the density function is just k of I. Now, what's the density function? It measures the density of pink points here. Right? Now, the density of pink points is clearly related to the profile of this Young diagram. In fact, it's easy to relate the density of pink points to the slope of this Young diagram, to the average slope. So eventually, what we will see in a second is that this Young diagram approaches a certain limit shape. So when theta gets large, the Young diagrams get large. And eventually, after normalizing them in some way, we expect to get a curve here. Now that curve is supposed to be related to the density function. So let me try to get this curve. I didn't put the contours of integration here, and I even forgot which one was the outside, which one. Oh, I have it here. Okay. So I had the V contour inside the W contour. Right? Was it right? Okay, let's try. If we don't get the right answer, then we'll think. Yeah, I actually have it the other way around. Okay, let me proceed and then we'll see. Let's imagine that these are, so let's say this one is, the absolute value is equal to 1, and this one is a little smaller than 1 minus epsilon. So the two contours are approximately the unit circle. Now, on the unit circle, see, this part here is independent of theta, right? The only thing that depends on theta is this thing. So on the unit circle, V minus V inverse is a purely imaginary number, right? Because this is, on the unit circle, this is V minus V bar, and so this is imaginary. So we have a highly oscillatory integral. We have E to a large number times a very oscillatory object. Now, the good thing about it is that this object has absolute value 1. So yeah. What am I going to do now? I'm going to try to deform these contours in such a way that the real part of this function here, gets negative. Now, if I manage to do that, what I have here is e the power theta times a negative number. So it's going to kill my integral. If I manage to deform my contours in such a way that the exponent here is negative in the real part, the integral is 0. Now, hopefully I won't be able to do that, because if I'm able to do that, my correlation kernel is 0, which is nonsense. So there may be some obstacles along the way. We'll see. Now, one thing I didn't take into account is where I want to compute my density. Right? So I didn't put the values I and I. Well, what I will do is that I know from some sort of easy considerations that the diagram should roughly live on scale theta. So this is approximately like constant times theta, and this is like minus constant times theta. And so what I will do, I will take this I to behave like u times theta. So I'm trying to compute k of u theta, u theta. So then this object here also gets the dependence on theta, right? So this is dv dw, v to, let's say, 1, so vw. And then there is a factor which is vw to the power minus u theta. So I'm going to put it into the exponential. Right? So I'll write here that this is minus u, this is inverse, right? Log v plus u log w. Okay, so this is equal to the double integral, blah, blah, blah. And then the important thing is here I have theta times some function in v minus some function in w. And this function in v is v minus v inverse minus u log v. Now this function is still, so again, I'm around the unit circle. This is radius 1. And so S of v is imaginary on the unit circle. On the absolute value of v less than 1. Yeah.
What is u?
So u is the point where I zoom in. So u is the scale which I use on the slides. Okay, so I need to know how the real part of this function behaves around the unit circle. On the unit circle, it's 0, right? Now, I claim the following, that if I look at the gradient of the so let me do the following. So let me look for the critical point of this function. So the critical point of this function, S prime of v, is going to be what? It's easy to, okay. So I'll just, this is v plus v inverse minus minus u. So when u is between 2 and minus 2, this function has two critical points on the unit circle. If I write u as 2 cosine phi, then I have two critical points, which is e to the I phi and e to the minus I phi. Right? So the statement that I want to do is that if I take my contour and I shift it a little bit inside the unit circle between these critical points and a little bit outside the unit circle on the other part, then on the pink contour, the real part of S will become negative. Well, this is an exercise in well, except I'm not sure in the sign. Let's see. So the formula that I have here says the following. Let me write the function. Oops, okay. So the formula that I have here is the following. That the gradient of the real part of f is evaluated at z, which is x plus iy. This is the vector xy multiplied by z plus z inverse minus u. So minus 2 cosine phi. You can just check that. Okay, let me not do the computation. This is an exercise in Cauchy-Riemann equations if you wish. You can just compute them. Sorry, this is not supposed to be f. This is supposed to be s. Thank you. This is the action. This is what sits in the integral. So see, this object here is positive. So this is positive on this part of the circle, and it's negative on this part of the circle. So if I move in the direction of the radial vector, my real part is going to increase on this part of the circle. So if I move outside, my real part is growing. If I move inside, it's decaying. So if I move inside here and outside here, my real part will become negative. Now I can do the same argument for the w, except for with w, I need the real part to be positive if I want my integral to die, right? So that means that I want to move my contour in the opposite way. So these are my target contours for V and for W. My original contours for V and W are like this. If I manage to move to my target contours, the integral dies. Now you see, when I move the contours like that, I need for the contours to pass through each other. If you go back to the formula for the integral, there is a factor here that doesn't like V and W being equal. Well, that just means that I need to pick the residue that corresponds to this factor. Now the conclusion is that this integral converges as theta goes to infinity to the residue. Now the residue is going to be integrated along the part where it's taking, which is this part. So the answer is I need to take the residue of the integrand where V is equal to W and integrate it along this part of the circle. That's all. So let's see what it gives. It gives the integral from e to the minus e phi to I phi to e to the I phi. Now the residue will cancel almost everything. In particular, this part is going to cancel. And so what I will get is dz divided by z. And then there will be 1 over 2 pi square root of minus 1. So 2 pi I here. So this is just going to be the sine of phi. Am I right? No, that's not true. So this is the log, right? Yeah, This is going to be phi over pi. You can check. So let's see. My phi was the angle on the circle, and phi was ranging between 0 and pi. So phi was 0 when I was at the right end, and that's where the density is 0. And it goes into 1 on the left end when the density of particles become 1. That's when the particles get dense. And the right end happens, so phi 0 corresponds to u equal to 2 cosine phi. And so that means that this is 2 theta, and this is minus 2 theta. And then my diagram is supposed to live between 2 theta and minus 2 theta, because on the right from it, the density of particles is nothing. On the left, the density of particles is 1. Right? So the density is not a complete solution to the problem, but if you follow the argument with the contour deformation, getting more detailed information is actually trivial. So here I computed the density. What happens if I now compute k of u theta plus a shift, v theta plus another shift? So that means that I'm sitting somewhere in the middle of where my diagram lives. And then I'm taking a finite distance to the left and to the right of it, and I'm computing the correlation kernel. So I'm computing the probability of pink points located at specific locations near a global point inside my limit shape. Right? Now what changes in the argument? Sorry? Yeah, that should be u. That's right. I need to be near the same location, because if I'm near different locations, I'll get a trivial answer. So if I do it like that, then what changes in my argument? Well, so the only thing that changes is here. Right? Let me take I get an additional v to the power x, an additional w to the power minus y. Now, if x and y are finite, this is not going to influence in any way my argument about the contour deformation. If I deform, I still get an infinitesimally small contribution, so I again need to pick the residue. Now, if I pick the residue, this will give me 1 over 2 pi I, the integral e to the minus I phi e to the I phi. And then instead of dz over z, I'm going to have dz over z. If v is equal to w, then these things give me x minus y plus 1. So this converges to, and this is sine of phi times x minus y divided by pi x minus y. The integral is elementary, you can just compute it. So that gives what people call the local limit of the correlation functions of the Venn diagram. That tells you how the pink particles correlate when you're in the middle of the Venn diagram. This is called a discrete sine kernel. It's a close relative of the continuous sine kernel, which arises in the limit in the local correlation behavior of the random matrices, of GUE random matrices. And actually, there is a proof of that fact which just goes along the same line. Once you get to the integral representation, there is a contour deformation argument that allows you to read off the answer in an easy way. Okay, but that still doesn't tell me what happens near the edge. Because what I started with was the last passage percolation time, which is the behavior of the point near the end. So far, this argument worked as long as my u was between -2 and 2. So that worked as long as I was enough inside the limit shape, the bulk picture. Okay. So then the final thing that I want to do is to get the behavior near the edge. Let's look at the picture. So what happens to contours near the edge? Right? So this is my unit circle. I have two contours. I have this one and this one. And the points where they cross have argument plus and minus phi. So when phi gets to 0, right, so phi is related to the density. The density of the particle, so the density is phi over pi. So when I get to the edge, my density will get to 0. And on this picture, what will happen is that these contours will have to come to a single point like that. Yeah, the other one will do that. Right, this is the point 1. Something needs to change, right? I don't have residues anymore. I need to do something else with it. Now, what changes analytically is that, well, clearly the two critical points of this function merge. So I get a double critical point at 1. And again, if I deform both my contours to what I just drew, then my integral will go to 0. And that's true. The correlation kernel near the edge goes to 0. And that's because the points near the edge, these particles, become rarefied. The distance between them gets large, and so the probability of finding a point near any location is 0. Now that's not satisfactory for us. We don't want to get 0. We want to get some scaling limit. We need to rescale the particles in such a way that we get a meaningful asymptotics. Okay. What it means in terms of the complex analysis picture is that I need to blow up this picture. I need to introduce a local coordinate for the integration near this double critical point. And I need to see how my exponential really behaves. So this is my, so now I have a double integral. Inside this double integral, I have e to the power of v minus v inverse minus log v minus twice log v. And then this is minus w inverse minus twice log v minus twice log w. So near v equal to 1, this function, so s of v, if you do the Taylor expansion, this is the double critical point. So in the first approximation, it has the behavior of the cube, right? So the first few terms of the Taylor expansion vanishes. And so if you want to look at the profile of how this function looks, this is something called monkey saddle. And I'm not going to draw it. Well, maybe I need this picture here. What I'll do instead, I'll do the local change of variables. So I'm going to take my integration variable v to be 1 plus theta to the power minus 1/3 v tilde, and w to be 1 plus theta to the power minus 1/3 w tilde. There was a prefactor theta here. So this is exponential of theta multiplied by this expression. So now if I do that, then e to the power theta s of v minus s of w is equal to e to the power theta to the power minus 1/3 v tilde cube not a good way to write it. 1/3 theta to the power 1/3 v tilde cube minus 1/3 theta to the power minus 1/3 w tilde cubed. Now the good thing now is that theta cancel from this computation, and so you get e to the power 1/3 v tilde cubed minus w tilde cubed. Okay? So the exponential now plays a very different role. Instead of killing the integral, in local variable, it gives a finite contribution to the integral. The integrand converges to something in the local variable, right? Now, when you change the variable like that, you'll have to deal with the fact that the differentials also change. And so that will produce a small prefactor that will show you the actual scale of the answer. Let me just tell you, without doing the change of variables in the full integral, what will happen. If I now take my arguments of the kernel, whatever they were denoted with, I and j. So if I take k to be 2 theta plus a shift of size theta to the power 1/3, and then the other argument to be 2 theta times y to the power plus y to the power theta to the 1/3. So that means I'm near the edge, but I'm taking a different, but I'm taking a shift from the edge of the size t to the 1/3. Right? And if I do that change of variable in the integral, then after I collect all terms, I'll get the asymptotic behavior that this is equal to theta to the power minus 1/3 double integral of e 1 over 2 pi squared e to the minus I v tilde cubed over 3, or maybe there is, actually it will be no I, minus w tilde cubed over 3 plus v tilde x, where x is this shift here, minus w tilde y, d v tilde dw tilde divided by v tilde minus w tilde. And what are the contours for these integrals? Well, they are magnified contours like that. So I'll have now 0, and I'll have a contour like that. That will be the contour for v tilde, and I will have a contour like that. It will be w tilde. And this is the behavior of the correlation kernel near the critical point. Now, why near the edges of the spectrum? Why is it useful? Well, if we look at the density function, we see that this is approximately of size t to the minus 1/3. So the particles are approximately spread out by the size t to the 1/3. And then finally, if I want to look at the probability that my first particle, lambda 1, is less or equal to something, so this is my last passage percolation time. Last passage percolation time. This something is better to take of the form 2 theta plus s to the power theta over 1/3. So this is the probability that the first particle is less or equal than that. By inclusion-exclusion principle, this is 1 minus the the sum of the first correlation function evaluated when x is greater than, well, this, so let me call this bound something. Let's say a. X is greater than a plus the sum xy greater than a rho 2 of xy minus 1 over 2 factorial, 1 over 3 factorial, the sum of the third correlation function, and so on. X, Y, Z. This is a general statement that holds for any point process. If one wants to evaluate the probability that some region is free from particles, then, well, you take 1 minus count all the particles that are in that region, then some particles are counted twice, you add that, and so on. This is sort of a general formula. This is inclusion, exclusion. And then instead of this correlation function, I plug in the asymptotic value. So this is just k of xx. This is the determinant of the 2 by 2 matrix, xx, yy, xy, yx, and so on. And once I plug that in, these sums turn into integrals. They become Riemannian sums for the integral of the limiting kernel. And eventually, this series converges into a Fredholm expansion of a Fredholm determinant. Determinant of 1 minus some limiting kernel that L2 on S plus infinity, where this limiting kernel A of xy is this. Is this formula. Okay. What's the point? Okay. So I've done the computation maybe too fast and skipped too many steps. The point that I was trying to make is that at this moment, once I have the formula for the correlation function, any question I want to ask about the asymptotic behavior of this Young diagram can be answered by taking the asymptotics of this double contour integral. Now, the asymptotics of the double contour integral is done through, can be done through the steepest descent analysis. This is the fancy name of what's written here. So arguments like that were popular in the 19th century. They're not so popular now, but they still work. It can also be done through other methods. But the point is that once the correlation kernel is in your hands, the answer to asymptotic questions are fairly easy to get. Or at least there is a path of how you can get them. Right? These types of arguments are common. Again, in most examples where the determinantal processes arise, there is some sort of an argument of this form. The original argument that was done for the Plancherel measure, again, is due to Andrei Okounkov, somewhere around 2001. Maybe before Andrei, there were also limits of this form, except for they were not done with contour integrals. I wanted to show the contour integrals argument because they are, in a way, the least technical. Right? And so this will conclude the part of my lectures where I deal with determinantal processes. What I'll try to do tomorrow, I will try to show the reason why, or maybe not the reason, but how the algebraic structures produce probabilistic structures. So far what I've done, I took some probabilistic model and I showed you a path through Schur functions, through these integrals of getting something out. Now I want to go the other way. I want to take something related to Schur functions and get probabilistic models out of it. And then in the final lecture, I'll take something more general and we'll show how to get the finite temperature polymers out of that. All right, so that's good for today. Thank you.
Excuse me, do I understand correctly that the formula you wrote for in this regime, so you don't really need the contours to be some specific contours, but the contours for v tilde and w tilde can be any contours going to infinity?
That is correct. You don't need specific contours. You need these contours to stay in certain cones in such a way that this integral converges at infinity, which is easy to achieve. You just look at where the highest term decays at infinity, and that's your region for the contours. Yeah.
So it's only for asymptotic analysis that you need the steepest.
That's all you need for the. I mean, you don't need actually the steepest descent where the decay is maximal. You just need some decay, and that's enough to do the analysis. Yeah.
Is there a simple way to modify that particle partition picture for the case when you don't have this infinite number of particles to the left?
What concrete example do you have in mind?
Well, like something like infinitely many gaps to the left, something like that.
Well, okay. So the GUE, the random matrix ensemble, can be treated in exactly the same way. Once you write the correlation for kernel in terms of orthogonal polynomials or mid polynomials, you can rewrite that kernel, the Christoffel-Darboux kernel, as a double contour integral. And after that, the argument that I just showed essentially literally translates there. And that may be seen as the reason why the answer you get in that case is the same as the answer I get in this case. There will be some details that will be different, but also, but again, there will be contours, critical points, and the deformation that takes you to the place where the contours don't matter anymore somehow, where the integrand dies. So that's an example when you have finitely many particles, you don't have the infinite tail of particles to the left.